Hi everybody. I'm happy to see you this afternoon. And today we're going to talk about predictive analytics when it comes to detecting some viral events and influential users. It can be social media influencers, it can be some interesting events that are happening around the globe. And of course, we're going to predict this from social media networks, which is a whole our course is about. So there's a couple of articles. These 3 articles are all published in very good conferences. You can see the CIR is ACM, WSDM, but also 3W. And we will be covering all 3, but overall, to really understand in more detail the details of today's course, I encourage you to read all 3 articles and dive deep. 1 hour is not enough. I will be just glazing through, but you could really understand the details from these 3 articles, which I encourage you to do. We're going to talk about event detection as a general, and about influential user detection, as well as about such phenomena called cascades. When you are getting some information gets spread across social networks. So let's start and overview about event detection and event detection framework. So in a paper that has been proposed, the framework of event detection from social media can look like this. You can see it involves a technology, so-called crawler technology. Then this technology collects the data, and you also have some classification technology, basically that ranks users, classify users, and actually it also affects back the crawling process. We have also the repositories and databases that get affected, that affect the whole result. We might also mine a social graph, because social relationship is quite important. And we can mine the sentiment, we can mine the topics. All this information pretty much is essential to do a high quality industrial level type of influencer user detection and event detection. So let's break it down one by one. Basically steps 1, 2, 3, and 4. Let's break it down one by one. So in the first step, we have this so-called data gathering, right? Data crawling. And we can use several types of crawlers: dynamic crawler, known account crawler, key user crawler, hot location crawler, image object crawler. Approaching this holistically is pretty much the only way for us to be broad enough and also holistic enough to really be able to find and leverage the events and influential users we want to look for. This kind of technology is used in so-called social listening platforms, and just look at it in this way. If you're a social listening platform but you're not listening everything, it would be similar to, you know, somebody listening a lecture but sitting in a nearby building and, you know, not hearing anything. So you must be sitting in a lecture hall to listen to the lecture, and that's why the framework social listening platform must also listen for a lot of data from different sources in order to be holistic and in order to monitor this data properly. So if you look into the different types of crawlers, you can see that you can crawl by keywords, by knowing a particular account. This is relevant to influencers. Key user crawler, which is similar, but it comes to individual users. Hot location crawler maybe can be related to, let's say, physical stores of a brand or etc. And of course, the image object crawler. So basically, this involves computer vision when we analyze the images and crawl, make decisions of what we crawl and how we crawl based on that information. Some remarks on data gathering would be around that data gathering is actually a key. Obtaining right data is a key for the right application. So that's why bigger the company, like Facebook or Google, they actually have access to more data, and that defines the leadership in the market. you could use APIs, but obviously those APIs will be only provided to the extent that API providers will make financial benefits for themselves from using this API. So they're going to give you the main treasure, the data, and therefore we can buy the data. But nowadays, with regulations around privacy, we're no longer really able to buy the data, and data selling companies are no longer relevant, no longer in the business. Therefore, we also can do data scraping, which is really pretty much about going through the internet, figuring out the content that's supposed to be read by human, but you can do it large scale by robots or by different accounts. These enhanced security measures, in order to scrap data efficiently, you might need to simulate the real user actions, and that boils down to the information that we were talking about in the previous lecture. So the actual border between legally scraping data like search engines do or do it illegally is actually very thin. So we always must be careful that we follow the law for the data source, for the data location where we do data gathering, and we have to be really careful about that. So, of course, the second part of event detection framework would be noise filtering. So, just crawling data is not enough. You really need to make sure that you filter the data that you crawl, and you want to remove the noise. And we was talking about this spam detection when it comes to detecting the spam and filtering the noise. We need to make it dynamic, so we need to update the key information, and we also can involve the influential user detection in this stage, so that we can dynamically and automatically pick up those accounts that provide most of these events, right? And enhance our crawling as well as use it as an application itself by finding the influencers in social networks. And also it includes this kind of viral events and cascades, which we'll be looking later during the lecture. So how would we do in event detection? Twitter, as you know, is very popular social network nowadays, and others are also quite popular. So just Twitter is easier to monitor because of the its open privacy concept and its publicity. So event, if you want to define it, is some reported occurrence at a specific time and place. So just something happened at a specific time and place, and that's called event. And events can be, let's say, real world events like elections. It can be accidents, it can be crimes, it can be natural disasters, it can be many other things. Per se, our lecture is also event, but since it happens every week, and since it's not like very keynote that opens new breakthrough discoveries of social media analytics that involves, I don't know, key government agencies and firms. We are not really event in the sense that we are just ordinary lecture about the social media computing. So our lecture is not event. But let's say if during our lecture I will be uncovering the knowledge nobody have heard about before, and I'll be doing it first time, and the press will be talking about this, then maybe our lecture can become event because it brings a lot of attention to the materials we will be disclosing. People often comment on events in real time, so it's like a feedback on the event, and even comments themselves can be events themselves in the future, right? So it's like a very dynamic nature of all this framework. So then you can detect the clusters of messages, for example, or even users. And this cluster detection step is crucial because it helps you basically to figure out which things are related and whether there is enough volume of these things to say that, okay, there is events taking place, and therefore we can say that there is events happening. You can approach this by using one of the clustering algorithms we discussed in the previous lectures. And to do so, you can represent, let's say, your tweets by a set of features. We can define some similarity measure, let's say cosine similarity. And when a new tweets arrive, you can cluster it in one of the existing form clusters, so that if too many tweets get clustered into the same cluster, then probably this cluster represents some event. That's how it works. You can use k-means algorithm. one of the simplest real-time algorithms can be used. You know how it works, so I'm not going to be talking too much about that. Yeah, but like you know that one of the key properties of K-means that is real-time dynamic clustering. So of course you'll be also facing some shortcomings. That it's not very efficient and fast algorithm. It requires you go through the big amount of data. And performance is linear. You need to know the value of clusters. So like it's like if in advance you will know that tomorrow there will be 6 major events happening around the world, like 6 major disasters. And you need to know this in advance. So this is like a really issue, right? You're not a god to know what will happen, where will be a earthquake and where will be a crime tomorrow, right? So this is a definitely limitation and doesn't suit real world settings when we define events. Then you need to have a good similarity measure that really fits your data and data representation. It converges always, but not necessary to optimal global optimal solution. So it's not a convex type of objective function, and it doesn't help you to find an optimal solution every time. And then of course it's only applicable when a mean is defined. So if you have a categorical data, that will be much more difficult to work with, and you have to find the other approaches like k-medoids and other type of the algorithms. When it comes to hierarchical clustering, the inference might be easier, it might be faster. And also I discussed this clustering before, so we wouldn't put too much accent on it. You would just only want to say that this method doesn't require the prior knowledge about the number of clusters, and it uses the distance measures as a clustering criteria. Yeah. So yeah, it's basically in the step 0 we have all the data, then it converges into some cluster in step 2, step 3, step 4, and then yeah, and then goes to the step 4. It can also go in divisive, like in another strategy. Then you go from all things in one cluster, and then you separate them into multiple clusters in each step. Step 0, step 1, step 2. So it's just inverse. This is 2 strategies how it works. And it requires 2 distance measures between items and also between terms clusters to linkage the data and to make decision basically whether you want to do a split or not. We can also have a topic detection algorithm, and this is very much industry demanded type of solution because it's real time. So you can do kind of a fast incremental clustering. So at each time point, you can order all the messages in time, and it will be considered each measure and determine a suitable cluster assignment based on some similarity function again, right? So you take a new message, you have some similarity measure, you compare this to other cluster centroids that you have. So you don't need to compare to all clusters, you only compare to those clusters that you don't need to compare to all members, you only need to compare to cluster centroids, like summaries of what this cluster is about. And then if your threshold is passed, like your similarity with one of the centroids is more than X threshold, or T, how it's called here is CJ, right? Then you can assign this new tweet to this cluster. And if it's lower than threshold, then new tweet becomes its own cluster. So it kind of doesn't require you prior knows the number of clusters, and the clusters get pop up by itself. So if over time you're getting some event happening and the messages are all similar to each other, then you will end up having a separate cluster related just to that. And you will see that event if your data is sufficient. There was some research done, and the papers are listed in the beginning. So those papers were focused on the data set about StarHub, DBS, and NUS. These are 3 companies in Singapore. And inside the data set, there were topics. About StarHub, it was 24. About DBS, it was 17. It's like a big corporate, so it's quite a big number of events there. NUS is a university, everything is calm. There's academia, so it's only 5 emerging topics happening inside there. Yeah, so they were using 10, 8, and 2 emerging topics for training, and then the rest was used for testing. So this is the accuracy of a prediction based on different metrics, right? You can have a Twitter monitor method in the SIG mode conference. You can topics over time, a CKDD conference. You can sort dictionary learning based schemas and ACM-CIKM 2011, and there was a CL method. Obviously, it was one of the best methods in every case that was proposed by the authors of the paper. So now let's talk about hot emerging topic detection as a whole, and then we want to predict hot emerging events before they become viral. Because honestly, if we only can detect events, this is useful, but not as useful when it comes, let's say, for predicting a stock price based on events, right? But if you see that something is going to happen, you have access to this real-day data, maybe you can try to predict this in advance. And if you can predict this in advance, you can make actions upon these events really in advance. And then maybe you can get some financial business benefits out of that. Let's say you can buy some stocks before they grow, or sell them before they fall down, right? And those growth and fall down will be dictated and reflected by the event that you're trying to detect from the Twitter. So this is like a scenario. So you are at the time TS, and the event will become hot at the T hot, HOT on the right side, but we want to detect actually the TS. So there are many features can be used for that, and I encourage you to go into paper to achieve a high accuracy. But you have seen these features before in the previous lectures, and I was breaking them down. Basically, the level of retweets, the volume of the tweets, and many others. In the right bottom corner is papers that talking about these features, so I encourage you to download the paper and see the description. If in your work that you are doing for your final project, you want to do hot topic detection, I really recommend you to address this paper and see whether they can actually leverage on this feature in feature engineering and apply some more comprehensive deep learning approaches on the bigger data to even improve the performance that they already had. The authors of this paper were using SVM, so it's like pretty much a standard, especially in 2012 approach, like support vector machines. Again, we discussed it before, so I'm going to spend more time on it. You can see that the topics were predicted based on a small number of tweets. So the topic threshold was happening in around 10. And you can see that different topics were starting from a different events, right? So you can see different number of tweets in the beginning. So some topics were starting. Topic 3 was quite a while in a small level of tweets, and then after that start growing. Some topics grow immediately, and this also shows the different nature of the topics. Sometimes it might evolve very fast. Sometimes it might evolve slow, but then get some significant boost, and then it become famous. How it happened in social networks like in LinkedIn. Usually, if it doesn't have too much engagement in the beginning, it doesn't have much time, doesn't have much chance to be very popular in the future. But if it get a lot, like the red line in the beginning, then it has chance to become big quite fast, because the social network will be promoting this topic to the users. So what it means? It means the social networks themselves also use this topic detection scenarios to basically figure out which hot topics are emerging inside the system, to assign a scores to new posts and topics, basically to decide whether this content is of interest to people and it needs to be provided and promoted to other people. So yeah, there was a topic in US Fire, so many people talk about it, just immediately start talk about it in 20, it started from 20 tweets, everybody started to talk about it. Then there's another topic that gets a very high spec, it's a government public cloud related topic 3. And there is also confirmed iPad mini, and also a new cable TV topic for the telco provider. So just a couple of case studies, you can see how the topics work. We have a 5-minute break, and then we continue on the remaining 2 sections for the today lecture. Okay, so let's discuss how can we use the topic technology to discuss influential users, influencers, and other people on social networks that can be used for your marketing campaigns and for other purposes. So, what is topic-based influence? So, the motivation of this is a number of followers is a main metric to identify influential tweeters, and at the same time, tweeters' influence may vary with different topics, and also sometimes we can get fake followers. Sometimes we can get people who doesn't post nice, well-prepared content, so the influence would decrease. So nowadays, even influencer marketing, you know that people quite often don't rely on the number of followers, because number of followers even doesn't guarantee you reach anymore if content is that good, but rather go for the engagement rates and this kind of important metrics that you can really rely on when deciding on how influential this user is. And approach this paper proposes in early 2010 in WSDM conference is how to identify influential features, taking both the topical similarity between users and also link structure of the social graph into account. So they used dataset of about top 1,000 Singapore-based tweeters, and they had 196 people inside. They crawled up all followers of these tweeters, and they end up getting 6,748 followers together with tweeters themselves. So basically, they crawl the social graph, the hierarchy, and they also crawl the tweets that user have published so far, which was about 1 million, slightly more than 1 million tweets. So they found immediately interesting observation that 72% of the tweeters follow more than 80% of their followers. So we usually follow our followers, and 80.5% of tweeters have 80 of their friends follow them back, right? So it's like two mirrored measures pretty much. So the graph is quite dense. People follow each other, even though Twitter is one-way social network. People tend to follow each other back very often, unless you're a superstar, then you will be doing that. Are users following relationship more similar than those without, according to topics they're interested in? Like basically, do we follow people based on the topics or based on the relationships? Actually, this was first research question. The second question was, is there reciprocal following relationships more similar than those without, according to the topics they are interested in? And they did some statistical analysis, and also they found the phenomenon of homophily on Twitter. I'll explain what that means a little bit later. So they were focused on topic modeling, and they were aiming to identify the topics that users are interested in based on the tweets they have published. And they used Latent directly allocation model for this. LDA is quite common model, and it's a generative statistical model that basically allocates, given a number of topics, it distributes each of the users across, or user content across the topics this content will get published. So basically, you have a document, and I'm telling you that this document is likely to be about topic A, topic C, and topic D out of, let's say, 20 topics. 20 have to be defined by us, right? So we have to say it's probably 20 topics inside, and the algorithm will iteratively go through the generative structure to decide how many topics are there. So this is a little bit more detailed breakdown. So we can have users of dimension D users, and we can have T topics, and then user tweets get all put together in the user level. So it's like one document, and you can basically distribute each of these users among topics they discuss, and these topics can be detected from all their content that they posted. So they totally posted maybe 1 million tweets. You put all these 1 million tweets batched into by user grouping into the algorithm. The algorithm can figure out, okay, there's probably 20 topics inside, and each of this user most likely was talking about these topics the most. This also means that each of the user have the vector of size 20 that basically shows, okay, these guys will most likely, more probably talk about these topics, this guy more probably talk about these topics. etc., one by one, right? And then to the end, we are getting the results. So then we can also define the topic difference. So of course we can define it by difference between users by measuring similarities between these vectors. But we also can define the topical difference, like how one topic is different from another, and we can do it by one of the probability distribution comparison functions. So one of them is called Jensen-Shannon divergence, and it's defined here. So we have distributions, dty, dtj, and we can compare the distribution one to another. So typical difference between two users usually can be computed as this DJS metric between these two users. So now we kind of get in a graph, right? So we can compute the topical difference between every user, depending on which topics they are talking about, and then we can see the difference between them. Then we can define the so-called Twitter rank function. Why it's called Twitter rank? Because it's similar to page rank that search engines use. Search engines, they use explicit links between websites to define this page rank, this famous Google algorithm page rank that Google starts from, and also we can have a topical differences for Twitter. And it integrates two components into transition probability of surfer from follower as I to friend as J. And then this probability can be defined as you can see it on the slide. You can see more details in the paper. Then the topic-based similarity is defined in the second part of this equation, right? Just in the way I described earlier, but with one minus to convert the distance function into similarity function, basically. Then if you go further, then aggregated Twitter rank of a Twitter user I can be defined as a sum of this Twitter rank times RT, and that RT is a weight associated with the topic T. So it's a weighted similarity, and it's just basically linear combination. You can see because it's a sum of weighted topic ranks. Yeah, so we can define a topic rank of particular Twitterer. Now we are done because we know a rank of each person, and we can basically decide how cool or how popular, how influential this person is. Just same as Google decide how influential the web page is, and then decide the ranking of showing this web page in a search engine output results. Yeah. So this is just a formal definition. It's taken from the paper. So we said the Twitterers who publish more than 10 tweets, so they have chance to be popular. The ground truth is existing following relationships in this data set. And we can also define a set U, is existing polar relationship minus the follow links. So we get a set of 10 random filters around that they might be follow, and then we apply different algorithms to predict whether one guy is going to follow to another and compare it in ground truth, right? So basically, we just randomly pick up people out of the data set, and we're trying to figure out, can our algorithm actually predict whether this following will happen? And the following particular user basically means in our ground truth that this guy is popular, has a high relationship in this whole graph that we built. And researchers have set up the experiments. They had in degree baseline, basically in the degree of the graph, of the edge of the graph, of the vertex of the graph. They also set up the PR, the standard page rank. So this only considers the graph itself. It doesn't consist of the different distributions. They also have Twitter rank, the proposed algorithm, and they incorporate topic-specific influence in the page rank. So they took a page rank and put a little bit of influence related to specific topics, but that was not Twitter rank, not specific Twitter rank approach. And then they also measure the quality of recommendation. So basically, how likely they were able to predict that the actual following will happen in ground truth by just looking at particular graph, particular vertex, Twitter, and deciding how likely this guy gonna follow another guy, comparing it to ground truth. So they found that actually, based on this ground truth of related follow relationships, this Twitter run gets very good results, and across different metrics, right? So it was proved to be very effective. And again, you could learn more about this paper and experiments from the paper, and we will just go further and let you talk about the cascade detection. So cascades, or basically we just talk about more general things, content diffusion, social networks. It's all about the relationship between people. How this, that's why it's called social networks, right? So social networks enable diffusion and flow of information. So we talk to each other, we communicate, and that things get spread. So cascades from people are formed when the information gets reshared from one person to another. Like you posted something in LinkedIn, somebody reshared, then that guy was influential, get reshared. So we basically try to figure out how likely this information will get cascaded in the social networks, and therefore how likely this information need to be also propagated by the social network itself. So this kind of cascade detection approaches are quite common algorithms that social networks like LinkedIn actually are using in their own backend infrastructure to figure out whether your content needs to be promoted, needs to be shown, how many impressions it should receive as compared to other content. It's very important for them because they don't want to show wrong content or don't want to show not engaging content to others. A few examples. A chain is defined according to different actions users can perform on the items, right? So as in Twitter, it can be retweets, Facebook can be shares, and Flickr, it can be like a favorite the photograph, and there's a couple more examples in other social networks. For example, for Instagram, what it can be. How can a chain be can be spread? Well, probably based on the comments, right? Because a comment is explicit reaction, not particular post, and therefore, if you commented on it, it can be created a link to another place, and you can define it by yourself. Doesn't really matter. The point is, in different social networks have different definition, and the questions and problems you want to solve is whether the information gets reshared, will popular content remain popular, what do large cascades look like, and how will a cascade grow in the future. And if you want to apply it to the real world problem, let's say in influencer marketing, before influencer post the content, we kind of want to figure out how likely this content going to be popular. Because how popular it will be will define how much engagement it will receive, how many eyeballs will see this content, and therefore what will be the revenues of this brand who uses influencer to do advertisements. And the same problem gets solved by social networks when they do paid media campaigns, very similar. So now we want to figure out, well, in this scenario, how likely this post before get posted get viral. So this kind of cascade prediction technology can be very useful here, because if the likelihood is high and the post is good, if the likelihood is low, probably we can reconsider redoing the content for this particular blogger or choose another blogger actually to run our influencer marketing campaigns. There's the changes. So large cascades are quite rare. If you see the distribution, so you need to kind of have a data to have a different data to large data to train the models, supervised models. But also you can see the same content that have a very different popularity being posted by different accounts, obviously, right? Sometimes some superstar post completely not relevant content, but it's get very popular just because of this persona. But also at the same time, we might post something very nice content by an unknown account and it won't get any popularity. So this is an important part, and this basically means that the profile of the user and also the social graph around the user is very important. We cannot just judge the content itself. And if you want to formulate the problem, given a cascade that currently has a size of k, predict whether it grows beyond the median size of fk. And fk and the median size of all cascades is at least k shares, right? So basically how much it will grow. So we have less than a median, more than a median example. And our current situation has a left side. So on the left side, you can have cascades of 3 reshares. So k is equal to 3, and then you get one more and one more reshares, and that's not considered to be a popular cascade development, but at the same time, in the second case, you can see that cascade have grown a lot because it become one more cascade there. And also another problem is who should be that node that I want to share my content so that it will get propagated in the network. So if we are able to define these influential users, find them, then that solves the problem of influencer marketing search, not just by number of followers, engagement rate, but rather on the social graph and historical information about how well this content be engaged in the audience to the brand. So how to predict popularity? You can do it based on content, user structure, like basically a social network graph, and the temporal metrics. How fast is that? All this information is very important, and you could notice that when you post a post on LinkedIn, it's not just about content, it's not just about your profile, but also it's about your current social network structure that doesn't change much, but also it's about the time. Therefore, let's say don't post your content at night in your region, post it in a time when people are gonna watch it, when social network have a way to show this impression to people, and the temporal aspect will really help you to do this. But also, if you look at the content itself, you can see that the first content get probably more popular about extreme surfing, and right content about like C++, some programming languages might be only popular on some certain communities. I don't know, programming geeks, but also the quality of content is not so nice. There's some background before, the images are cut, the images blur. So left content could be more popular than the right content, but however, if this get published by influencer users, it could be a different story. Overall, in content features, we can talk about the hashtags that I used, topics that that detected for this content. You can use an LDA topic to process the text. A sentiment of text on the image properties like some visual concepts, color histogram, the edges, the back of visual words, the convolutions if you use convolution neural networks, and of course, there's other factors such as whether this item was posted to the right community in the right time, in the right direction, in the right place, etc., the context. And the user features, of course, we'll be talking about follower count, right? How many people follow me is quite important. And well, if they're active, they're not bold, then this also will help. So it's my activity per day, but also it's activity of my followers. How many this was previously reshared and counts of reshares. So this is particularly very important for LinkedIn and Facebook. If something gets reshared, liked, commented, especially very fast, and there's a high chance that this post will get viral and get more reshares because it will get shown to more people. Again, LinkedIn decided because it thinks, okay, there's a cascade forming there, probably interesting content because people react on it. Therefore, it's relevant to more audience. So choose which audience to show, and I'll try to propagate that. My LinkedIn network right now is around 17,000 people. Yeah, so it's like 17,000 followers in my LinkedIn. I guess if I post some well, just normal boring content, then I might get around 500-600 impressions. So 500-600 people will see. But if during the first few hundred impressions, there's a big number of commented it, reacted it, or reposted that, then my content can be shown up to 4,000 or 5,000 people, right? So it's like at least like 30% of my followers will see this content. And it's important that my account has its followers, but it's also important the content itself and the other features. So structural is about the quality of my network and who people are following me. So my LinkedIn network is mostly consists of researchers, business people, marketing people. So if I'll be talking about machine learning, then only maybe research chunk of it will be talking about it. And if it's just like some general problem or business application of machine learning, then business people will not be deep enough to like it, and machine learning people will be too not interested of talking about some basic machine learning applied into business. So therefore, I might get both communities not engaged, and therefore some might get lower initial reach, and this post might not go very far. Therefore, my posts about marketing topics, my posts about business topics actually usually get much higher engagements compared to my posts about machine learning topics. Yeah, this is just a very good example of how the this works. And yeah, depending on the structure of social network, features can be extracted from two types of subgraphs, right? So it's a share subgraph, the first k shares, and also induced subgraph. So the friend subgraph was the first k shares, right? So basically, the extended network of the second order compared to what it gets reshared. We can compute out degrees of each reshare, out degree of each reshare on the second graph type, and of the subgraph, right? The whole graph, the reshare graph, induced subgraph, and also how many users reshareable, and the number of edges. So this all the features can be used. And yeah, this is useful features. Temporal features, of course, talk about time between a regional post and the ICE reshare. And yes, this is what just explained, super important. You get it in the right time, people see it, people reshare, it actually contributes chance that social network will show more impressions to people who are likely to watch this post in the future, and also average time between the shares, like how fast people react, the ratio, like conversion, the action rate, how many people really shares compared to everybody who have seen this. Average time between the shares, etc. As many things, and basic intuition behind this: the faster the action happen, larger the cascade will be, and therefore more social network will be encouraged to show the information. There's some results. You can see that all information about but temporal information gives you performance of 72 in terms of the accuracy at first 5 items when it comes to recommendation, but just adding this temporal into there helps you to get more performance by, I think, roughly how many percent? Yeah, something like 6%. But then you took just temporal, and you see that it's almost the same as everything included. So what it means at least for logistic regression, temporal features outperform others, and it's very important. So therefore, once if you want your content get viral, make sure you have a network of friends who can reshare, like, and meaningfully comment your content. Social network will be a key for your engagement rates. If you have a constant network of people who get nurtured to react on your content, then that's a key of getting much more impressions in social networks for free if you want to become a blogger or influencer. And many companies do that. They just ask all employees to share and react on the content they post. So yeah, just a little bit more information on cascades, not that interesting. So internal structure is very important. So you can see different types of graphs. The very first one is just get shared to one by one. Is a single side cascade, and then in the beginning friends are not interested, but only your friends were interested. That will be spreading only to your network. So that the right type of cascade probably means that that this is some information that where your particular personality and the fact that they're your friends get cascade. So for example, let's say the right cascade could be the result of, I don't know, you get a baby, right? And you share to your friends. Your friends really care, yeah, and that's why that is the reason why everybody react. But then in the right side, there's another situation when it's like very narrow community. Let's say you're posting about your dissertation and you have just, I don't know, very few friends that work in this area, but once it gets fit into that community, get propagated. But that's not very common for your friends, right? So then there's an example of a left extreme example of another cascade. Yeah, and you can predict the structure of cascades by running different algorithms. You can use a binary index, mean of length of the shortest path between all pairs of vertices. You can observe k nodes and predict binary index and about the median. Yes, that will mean that it will grow and be able to achieve a prediction accuracy of about 0.7 and an area under curve about 0.8, right, of predicting binary index. So this will basically show you the shape of a cascade. And this is again important, right, because social network can, based on this prediction and probability, can actually decide how it will propagate it. Whether it will be showing to friends, or let's say LinkedIn will be showing to all users according to probability that people will be interested. Cascade structure is very important. Ex-Ante predictions. For some applications, prediction must be performed before observing the cascades, and well, that's exactly what I'm talking about, let's say in social media. And of course, this is very important application. So if they can predict, then they can really decide whether this content needs to be propagated or opposites have to be hidden. So we have a user features. We have some object features and sentiment features from what the user has posted. We have models that can predict the popularity of this content by these users. And then if you can predict this popularity score, then by this user with this particular content, this is very useful implication, and this is what social networks are really doing. And it's called, in research terms, called Ex-Ante prediction. So overall, this is many papers and many interesting scenarios of where you can detect influential events or users in social networks, and this is very good topic for your final assignment when you do it in groups. On my side, we discussed all this today, and I really encourage you to read the papers to understand details better. In the next lesson, we'll be talking about graph theory in social networks, and that will talk about, we will focus about how to really detect this influential users, not from a like multimodal content perspective, but more by some graph structures, what type of structures exist, how these structures related to the ability of content to propagate. This kind of research is also done a lot, but usually not in real world data sets, but rather by synthetic data sets, unless you are Facebook or VK or Yandex or probably VK, right? Yandex on social network, VK, Facebook, Instagram, and other social networks that have whole graph, so we can do this research, do this study. There is one researcher in Finland. His name is Sandro Fortunato, very famous on this topic. If you really want to prepare well for the next lecture, you can go Google Scholar his research and learn a little bit more about the graphs. There is a mini project. It's an open assignment designed for you to freely propose social media project or app that you like to do. It has to be useful. It should be fun, interesting, and most importantly, it has to be, again, useful for solving some problems that the industry has. It's doesn't need to be complicated. It can be more like a MVP to see, and it can be implemented by technologies that we taught in our class and tutorials. It can be a mobile app, it can be web-based. And for those projects that are really cool, I will be able to bring it to ITMO accelerator or pre-acceleration program to present it and see whether it can be a real business in the future. So for mini project, we are targeted at end of November. Okay, so group details have to be sent much earlier. Sorry, this is a mistake. It was the first time, but then we will be talking about the end of this, end of November. We will be already pretty much hardly working on this project, and by end of December, you're gonna present. This is all indicative timelines. The actual timelines will be taught to you by Chiang today and other lectures, after other lectures, so that you can really start working on this project earlier, because the scope of each project has to be bigger than a lab works, and there will be also several people working on this project. Project is very important in terms of valuation. We are considering to make it be contributing 14% of the course, but for some years when we don't have exams, sometimes we make the project contribute up to 50% of the course. This is really individually for each year, but make sure that project will really play a very important role of your final mark for the course, and we'll be also initiating you by additional extra marks for really excellent projects that are not just good in technology, but also really viable in terms of business. So there also will be a presentation by instructors, by us, and also by voting among you for each of the projects, and out of that we will be able to come up with your final mark. I'm going to finish here, and let's have a little break, and after that you can continue with your questions and information about the current and outstanding labs and other questions that you may have. I'll pass it to Chi Yang, and have a good day. Bye.